the show on the road here. At this point, I think I've assigned up to 56, I think, although I told you guys last time I don't think you could probably have gotten past 43 or something. Start with some questions. Does anybody have questions from homework or whatnot? Happy to take a couple here at the start if you have anything. If you don't, that's okay. I know that probably most of us were worried about getting our stuff done that was due on Sunday and probably haven't taken a hard look at the new stuff yet. But Nick? Yeah, sure. Okay, so on, say, let's do 26. So it asks us to do F compose G of X. So I know from my definition of composition, that's just F of G of X. And G of X in the problem is 1 over X. So when I plug 1 over X in for X, everywhere where there is an X, I'm going to replace with the 1 over X. And then to square a fraction, I just square the top and square the bottom, right? So 1 squared is still 1, and X squared, well, that's just X squared. So there's the first composition. It also, the directions ask to do or compose F. So kind of the same way. So again, I know F is X squared minus 3. So if I'm doing G of X squared minus 3, I'm going to just be plugging that X squared minus 3 in for the X on F. So instead of 1 over X, I'm going to have 1 over X squared minus 3. Does that feel okay, Nick? Okay, Joey? 39? Sure. Sure. Since, Nick, you just wanted any of those, right?
Yeah.
Okay. I just picked one, kind of arbitrarily. All right, so 39 asks you to do a whole bunch of stuff, right? So part A wants to know if this is a function or not. Well, what's our answer here? No, right? And it just fails the vertical line test. B asks for the domain and range. Okay, so the domain is our set of x's, right? So I'm going to go look at my graph and I'm going to find the smallest x on the graph, which would correspond to that point right there. Does that feel okay, Joey? So if I count, that's what, 1, 2, 3, 4, 5, 6, 7. So the domain here should be starting at -7. And then the biggest keeps on going to the right, so to positive infinity for my domain. Okay, could be 6. It's hard to tell. It's small. I guess I could let's see.
Why is it
1, 2, 3, 4, 5, 6. Oh, why is it in a bracket instead of a parenthesis? Because this is the point, -6, 1, right? So there's definitely a point that uses that x value, -6. If I do the same thing for the range, I find my lowest point. Well, there isn't one because it's going down forever. And I find my highest point. Well, there isn't one because it's going up forever. So the range should just be all real numbers there. C then asks, is it 1-to-1? To do that, I'm going to use the horizontal line test. So that definitely passes the horizontal line test. There's no horizontal line that will intersect that thing more than once. And then predict if the inverse is the inverse relation is a function. Well, yes, since f is 1-to-1, f inverse is a function. And then part E says to find the relation or the inverse as a graph. So I'm going to just do that on the same picture here. Is that okay? And let's see. That looks like a good one to choose because it looks like it's right at an intersection. So that looks like it's 2, 1, 2, 3, 4. So I'm going to just kind of read some points off the graph. Let me put that over here, though. All right, so I'm going to start by plotting, instead of 6 or -6, 1, I'm going to plot 1, -6. And then instead of plotting 2, 4, I'm going to plot 4, 2. And instead of plotting, well, that's not -4, that's -3, huh? Instead of plotting 2, -3, I'm going to plot -3, 2. Okay, there's that. And now I know that this was my vertex, so this should also be the vertex. So I'm just going to kind of draw through, and there it goes. Same kind of shape, it just kind of rotated a little bit. Does that feel good, Joey? Okay. But that's the gist. So E is just the picture. Alondra? 42? Sure. So 42 is just a set of ordered pairs instead of being a graph. Honestly, that makes life even a little bit easier. So definitely a function, right? Because none of these points share the same x coordinate. Really cool with that? The domain, well, that's just going to be the set of x's. So if I just list my x's, I can do that just using the squiggly brackets. And the range, well, that's just the set of y's. So kind of doing the same thing. So far, so good. Well, it's 1-to-1 because, again, we have no shared y coordinates. And yes, that since f is 1 to 1, f inverse is a function. And then to draw this, I'm just going to draw with the flipped coordinates, right? So instead of drawing 6, -5, I'll draw -5, 6. And then instead of drawing -2, 4, I'm going to draw -4, -2. 3, 3, just, well, that's still 3, 3. 1, 5 becomes 5, 1. And then -5, 9 becomes 9, -5. And that's it. So, looked weird, but it's like, oh, it's just a discrete thing. But that even makes it easier, right? Everything is easier if it's discrete. Because now we're just swapping coordinates and listing coordinates. That's a lot easier even than when it's continuous and like anything is possible. All right. What do you guys say? We keep on going here? Oh, Hunter. 34? Sure. So I think it's the same questions, right? So if we're looking at 34, this guy, not a function because we have repeated x's, right? The domain is still just going to be a list of x's with no repeats in there. Notice that I'm not writing 1 twice. And the range is just a set of y's. Again, I'm only going to write 3 once. Cool with that? And again, the order doesn't matter. So whether you went biggest to smallest or just the order they appeared, whatever. Both are equally correct. It's not 1 to 1 because, hey, we got some repeated y's. So we can say since f is not 1 to 1, f inverse is not a function. And then E just wants you to rewrite this, the inverse. So to do that, all I'm going to do is swap the x's and y's. And I can see right away that, yup, not a function because those repeated x's now turned into those repeated y's from f turned into repeated x's in f inverse. And there we go. Does that feel okay? Okay. Again, like the discrete thing almost becomes easier than if it's continuous, right? Like it's just a little bit, like everything's a little clearer. There's less ambiguity. It's easier to see the things because all you're doing is looking for repeated x's and y's, and it's kind of, that's all she wrote. It's very easy to see what the x's and y's are because it's like literally written. There's the x's that we used. Those are the y's we used. Joey. Well, I mean, it's like the same thing as the other one, the 39, but sure. I'm going to do it a little less thoroughly. Is that okay? So clearly this is a function, right? No issues there. Agreed? The domain, if I do that, I pick the x that's furthest to left. Well, that's negative infinity. And the one furthest to the right, well, that's positive infinity. If I pick the lowest y, well, that's negative infinity. And the highest y, well, that's positive infinity. So there's my domain and range. Cool with that? Part C was if it's 1-to-1. Well, definitely not, right? Fails a horizontal line test. And because of that, I know since f is not 1-to-1, f inverse is not a function. And then D is asking us to write the inverse. So what I would do is I would worry about, I'm going to use those 3 points that are my x-intercepts. Those will now become my y-intercepts. And then I'll worry about like this one and this one. And I think after that I should be okay. So like that becomes -6, 0, and I end up with negative. All right. So yeah, that's -6, 0. That's -2, 0. So 0, -2. And that's 1, 0. So that becomes 0, 1. And that looks like what? -4, 10. So I need 10, -4. Okay. So we're going to come in like, and then where's my other one at? Oh, it's here. That's right, because it like duplicated it. So it kind of goes like that. And again, if you didn't feel good, if you draw in like y equals x, that now is like, hitting all the places. That all looks good because every place where the two intersect, f and f inverse, y equals x also intersect. So I feel real good about that. Does that make sense, Joey? Again, it's about like just trying to simplify what's going on. Just like I'm going to just turn this into a couple of points, swap the points, and then connect my dots. So not too bad. There's E. How's that feel here, folks? It looks really easy when I do it. I know it's not really easy when you have to sit down and think about it for a minute, but it's one of those you just have to be careful, right? Just have to be careful. All right. Let's pick up where we left off in 1.7 then, right? So I think the last thing we had done in 1.7, was something like, or was this example, I should say, something like this. I think it was exactly this example. Oh boy, that's really zoomed in. Does that look right to you guys? So since we've already done this once, but I'm going to do this again just so that I can kind of talk through those steps for finding an inverse algebraically, so that we hear those again and again, because it's the same steps. It's just going to be the algebra involved might be a little different, but the goal in each of these steps is going to be the same. So my first step is to abandon the function notation, replace my f of x with just y. After that, I'm going to use algebra to get the x by itself. And this is the part that, depending on what the equation looks like, could be really different. But basically, what we're doing when we're trying to solve, like get the x by itself, we're just going to be running the reverse order of operations. So instead of like, when we simplify, we go this way. When we solve, we're doing the opposite. We're trying to undo something. So we go the reverse. So the first thing I'd want to do is undo my addition and subtraction. And then undo my multiplication and division. Now the x is by itself. That's step 2 accomplished. Everybody feel good? Step 3, I'm going to swap the x and y's. And here at the same time, I'm going to rewrite this so it feels like the natural way to want to write that, where the y is on the left. So just kind of like flip the sides. Everybody's okay with that? And then my final step would be to put this back into function notation. So now instead of y, this becomes f inverse. Everybody feel okay? That should look familiar. We did that same example last time. So we have these two functions here, f and f inverse. How do I know that I actually did that correctly? How do I know that I got that those two things actually are inverse of each other? Ooh, the graph can be deceiving though, right? Sometimes that graph looks good, but sometimes it doesn't. Let's think back all the way to last time, and I know that was like probably almost a week ago with the 4-day weekend squeezed in there. But if you remember last time, when we started introducing this, we gave this algebraic definition for an inverse. Right, that if f compose g is equal to g compose f, and both of those simplify down to x, we've got it. That those two things have to be inverses. Let's use that to actually verify that what we got is the inverse of what we started with. And here, before we go, are we good with why those two are equivalent representations? Right? One of them just has a common denominator of 3, and one is written as two separate fractions with a common denominator of 3. Everybody's good with that? We can do with that. Either way is okay. And it doesn't matter which way you do it. It'll be the same either way. All right. So let's do the first composition. Our definition of composition says f compose g is f of g of x. And our g of x this time is 1/3 x plus 7/3. So f of 1/3 x plus 7/3 means I want to plug that in for the x in f of x. So I'll have 3, but instead of x, I'm going to write 1/3 x plus 7/3. And then I still have that minus 7. We okay with what I've done so far? Basically, this just went in for the x, right? That's all composition is. I'm plugging one function into the other. Now I want to simplify. So first thing I'd want to do is, in the order of operations, is to multiply. So what do I get when I multiply 3 by 1/3? What is 3 times 1/3? 1, so that just is x. And what's 3 times 7/3? 7. And then I still have that minus 7 at the end. And I know plus 7 and minus 7, hey, those combine to just cancel out. And I'm left with x, which is what I want. But this is not enough. The definition of an inverse says I have to check the other direction of composition also. That I have to do this way as well. So our f of x in this problem is 3x minus 7. So now I'm going to be taking the 3x minus 7 and plugging it into the x for g. So I have 1/3, but instead of x, I'm going to have 3x minus 7. And then I still have that plus 7/3. I'm going to then simplify, so I'll start by distributing the 1/3 through. 1/3 times 3 is still just 1. And what's negative 7 times 1/3? How about just negative 7/3, right? And then, whoa, we got that plus 7/3 still there, and those two just cancel each other out, and I'm left with x. So yeah, those two are definitely inverses, right? That's our definition. So if the composition both ways simplifies down to x, that's all we need. We got our inverses. We're donezos. Everybody feel okay? The rest of today, we're just going to do some more algebraic examples of varying levels of complexity to practice and review some of these techniques you would have learned in Algebra 2. But we're basically going to repeat this exact same two problems over and over and over again with just different methods, with different functions. So we're going to find the inverse, and then we're going to check our answer. We're going to find the inverse, and we're going to check our answer. We're going to find the inverse, we're going to check our answer. We're going to do this for a while. All right? So here's our next example here, where we have the function h of x equals 2x plus 5 over 5x minus 8. Who remembers what we call a function like this? You would have talked about it in your Algebra 2 class. Starts with the letter R. This is a rational function. We call anything that's a polynomial divided by another polynomial a rational function. Does that ring a bell now when you hear it? Okay, we're going to find our inverse algebraically. Start the same way as we did the previous one. The algebra here is a little bit worse. When I say a little bit, it's kind of a lot worse. This might be the worst example. But I'm going to start the same way. I'm going to start by replacing the h of x with a y. Again, I ditched that function notation as my first step. And now on step 2, yes, Edu. Sure. On my next step, I want to try to get the x by itself. What's going to be a problem here? What? Well, how many x's are there? 2. Which one do I want to get by itself? I want to get, before I can get the x by itself, I have to get it into one place first, right? Right now, the x is in 2 different places. So this becomes a little bit more complicated than the previous one, because I have to do a lot of rearranging to accomplish that goal. So first thing I would do is let's get rid of the fraction, right? Almost never is that going to be a bad idea. What would I need to do to both sides of this equation to ditch the fraction? Great, multiply by 5x minus 8. So here, those distribute, but here, those things just cancel out, right? So far, so good. Now, again, my goal here is I want to get the x's in one place. So I'm going to get the x's all on one side and everything without an x onto the other. Now, 5xy minus 2x, are those like terms that I can combine? No way, Jose. So how do I write that then? Yeah, I just have to write it 5xy and then minus 2x after it. Same thing here with 5 plus 8y. Are those like terms? No, so how do I write that? Yeah, I'm just going to write it as 8y plus 5. So far, so good. Nothing too complicated yet. Here's the tricky piece. I have x's in two different locations. How am I going to, what can I do to this to get that x in just one spot? It's like a pre-algebra, algebra 1 skill, but it's hard to remember to do this in this context. Nick? Well, if I divide the x to the other side, then it's like stuck on all that other stuff, so like it's not getting right. Like you get it into one place, but then you have a lot of other work to do. But that's not a terrible idea because it does get into one place, right? GCF stands for, if I look at the left-hand side, what is the greatest common factor? X. So what if we factor that x out front? Yeah, this is still factoring. Do you guys remember doing that in like Algebra 1, pre-algebra? No. You likely would have. You probably even did a little bit of this even last year when you dealt with quadratics in Algebra 2. Now that the x is in one place, what would I need to do to get it by itself? Not subtract. What operation is going on between the x and the parenthesis? Multiplication. So to get that parenthesis out of there, I need to divide by, not x, 5y minus 2. I want the x to be by itself. So I want to move the other stuff out of there. So that stuff cancels. And now we have the x by itself, as I would hope. What's the next step in finding the inverse? Yep. Swap the x's and y's. And then my final step would be to rewrite this as, H inverse. We'll go back to function notation. Because the problem originally was h of x equals. No. No, there's no reason why it changed to H other than like when we read doing each step subsequent problem, I don't want to use F every time because then it's like, is it this F or is it the last F? And it, you know, like just trying to like make it easy to communicate by changing my letter for each different problem gets a new letter. All right. Now let's check. Right, we got our answer. So we need to do this. And we need to do that, right? So far, so good. We do both of these and they both come out to X, we know we're done. All right. So our definition for composition says that H compose H inverse is just going to be H of H or H inverse of X. And we know what our H inverse is. We just found that 8x plus 5 over 5x minus 2. And now this is going to get weird here, right? Because we're plugging that fraction, 8x plus 5 over 5x minus 2, into the fraction 2x plus 5 over 8x minus, or I'm sorry, 5x minus 8. So everywhere there's an x, I'm putting in this fraction. Yeah. Right? When you look at this. Do you remember what this is called? This would have been something you might have talked about last year in Algebra 2 class. When you have fractions inside of another fraction like this. You call it a complex fraction, is what you call this when you have fractions inside of fractions. It's not fracception. That's an Inception joke, which is a movie that was a lot more relevant 10 years ago than it is now. Great. Good job, Mr. Kulik. All right. So there's kind of two different strategies I can use to simplify one of these complex fractions. So I can either, like, simplify the numerator and denominator until I have a single fraction on each, and then divide the two fractions. I don't like that because it requires me to add and subtract fractions, means making common denominators. I think it becomes a lot more algebra and symbol pushing. Option 2 is that I can multiply the numerator and denominator here by 1, in a way canceling the fractions inside of the fractions. That, to me, sounds like the better option because it doesn't require ever making common denominators. It doesn't require, like, adding fractions, which I don't want to do if I don't have to. It'll get rid of the fractions inside a fraction sooner. That's the route that I would suggest taking here. So the question becomes, how do I need to write the 1 that I'm going to be multiplying this by to get rid of these fractions inside of fractions? Well, just like when we make a common denominator, we can multiply the top and bottom of a fraction by like 5 on top and 5 on bottom, and really do nothing because really you've just multiplied by 5 over 5, which is just 1, right? So we're going to do the same thing here. The question becomes, okay, how do I need to write this 1 so that that fraction, 8x plus 5 over 5x minus 2 kind of goes away? So this is the trick. I'm going to go and I'm going to look at all the fractions in this problem. And I'm going to look at the denominators of all the fractions and look for the least common multiple of those denominators. Do you remember least common multiple? That's like a pre-algebra term. You might remember doing that in algebra, pre-algebra. I feel like I'm yelling over the group work going on across the hall the whole time. Just starting to lose my voice, it feels like. All right, least common multiple of 5x minus 2, 1. 5x minus 2 and 1 is just 5x minus 2. Yeah. That's the other beauty of it, is it's usually really simple to come up with what you need. And now we're going to distribute this in. Everybody's okay with how I've gotten to here and what I'm about to do? All right. When I multiply 5x minus 2 to the fraction 8x plus 5 over 5x minus 2, what do I get? 8x plus 5, right? We all see that? If we don't, I can write out more work. But if we don't need to, I think what we've written here is acceptable amounts of work. And look what's happened is my complex fraction is now just a regular fraction. I didn't have to add any fractions together to get this to happen. I didn't really have to make any common denominators or do any of that mumbo jumbo. All I had to do was multiply, which is a pretty good deal. Billy.
Where's the 5 over 1?
So you're talking about this 5 here?
Yeah.
That is this 5 here. Because when I multiplied, it just stuck onto the end of it. And I'll distribute here on the next step.
Okay.
But I didn't want to do too much too quick.
Yeah.
Good question. Is everybody good? Next step will be to, let's go and do some distributing, right? I told you this is like the worst one. Okay, so I went and distributed everything out. Does this all look correct to you guys? Yeah, Billy?
Should it be plus 16?
Absolutely it should. I tried to play that same trick on you that I warned you that I was going to do all the time. Remember that negative sign when we're distributing, we got to take it with us. So that absolutely should be plus 16 down there. Just to be warned, I'm going to play that trick on you lots of times. I'm going to try to use it all the time and making sure that we distribute those negatives. So don't get caught. All right. At this point, let's combine some like terms. So 10x and negative 10, or I'm sorry, 10 and negative 10 cancel out. 16x and 25x is just 41x. On the bottom, I have a 40x and a negative 40x. And then 25 and 16 is just 41. Those reduce down to just give me x. Woo! Oh no, though, because we're just halfway. Because we still have the other composition to do. Do we have to do it? Yes. Yeah, you have to show it both ways. One way does not work or does not count for, or is not enough, maybe I should say. Okay, let's rock this and roll it. We've done this once. It's going to be basically the same idea the next time through, right? So all of the techniques here will be the same techniques. We just are going to have like different, slightly different steps or whatever. All right, so when I plug this in, I'm going to have 8. And then instead of x, I'll have the 2x plus 5 over 5x minus 8. And then plus, where is it? Oh, yeah, plus 5. And then we'll have 5, and then 2x plus 5 over 5x minus 8. And then I'll have minus 2. So again, what am I kind of doing here? I'm plugging this into those spots, right? Okay, next thing, we're going to multiply the top and bottom of this by something. What should that something be? Oh, Nick. So this is h of x from our problem, right? And so I'm taking this, and everywhere there's an x in h inverse, I'm replacing that with h. So I have the 8, and then I have the plus 5, and then I have the 5, and the minus 2, but instead of the x's, I have that fraction for h. Is that? Yeah, no problem. And again, the composition in this case is a little tricky because that's a complicated thing. You're trying to like plug something into that's complicated into something that's complicated, and you get an even more complicated thing once it's all in there. It is I understand. Okay. What we want to do is get rid of this complex fraction. What are we going to multiply the top and bottom to accomplish that? 5x minus 8. You got it, dudes. So when I multiply this to the piece with the fraction in it, the 5x minus 8's cancel, and I'm left with just 8 times 2x plus 5. And when I multiply to the 5 piece, well, I just have 5 times that thing. And again, when I multiply 5x minus 8 to the fraction, the denominator cancels, so I'm left with 5 times 2x plus 5. Oops. And then I have my minus, and when I multiply to the minus 2, I just get minus 2 times that thing, the 5x minus 8. So far, so good. We're on the down slope now. This should be getting easier than we've done the most difficult parts. We're just going to distribute things through here. So I have 16x plus 40 plus 25x minus 40 over 10x plus 25 minus 10x minus 16. Does that all look good to you guys? What's that? Yeah.
I told you.
Good. I tried to play that same trick on you again.
I didn't even look.
I knew it.
Good job, Khalil. Contrary to what it appears you are paying attention.
I knew it. Yeah, no, I
This
knew
guy's
it.
a plus or minus.
I knew it. No, I meant that.
All right, combining some like terms. So cancel, cancel, cancel. And we left with 41x on top over 41 on the bottom, and that just simplifies to x, and we're finally done with this interminably long problem. Yeah, that's pretty gross, right? This would be the worst possible scenario you'd see on like the homework or whatever. Would I put something this complicated on the test? No. Why? Because it gets in the way of you showing that like you understand how to show two things are inverses because of all the algebra involved and like the hassle of that, right? The previous problem, no big deal doing the compositions, and you accomplish demonstrating to me the same thing, that you understand how to check whether these two things are inverses or not. But this one is El Grosso. Yes, of course. Let's look at the next one here. All right, let's find the inverse here. So again, y equals instead of function notation. And then what am I going to want to do to get the x by itself here? Add 4, good. Then what?
Take the square root.
I wouldn't do that yet, because remember, we're going this way, so we want to get rid of that multiplication before we get to that exponent. So I would do that first. Okay. And now square root both sides. What do we have to remember when we do that, though? Excellent. So here we have x equals plus or minus square root. Notice when I'm writing this square root, I'm making sure that I write it big so the square root covers the entire fraction. If your square root looks like it's only covering the numerator, that doesn't mean the same thing. I'd have to make a deduction there on that. If your square root only looked like it was doing this, that's incorrect. Your square root has to clearly be covering the entire fraction, because the entire left-hand side, when we took the square root, was the entire fraction. Just to be clear, and give you guys a heads up of like, sometimes you write something, but it's not what you meant. And I want to point out too that like we have to be careful about that sometimes. All right, then we swatchy what we got going on here with our x's and y's. But what do you notice when we look at this? What's P inverse? What can we say about P inverse here? It got that plus or minus out front. It's not a function, right? That's kind of a bummer, isn't it? What we would like is, well, is there a way that I can like modify P in a way that I can get an inverse out of, or I can make P inverse be a function without really changing P very much? So that's kind of what we're going to explore here for a moment. We're just taking a slight diversion to do this. So remember, what do we need to have to ensure that the inverse of a function is also a function? What property does that function need to have in order to ensure that its inverse will also be a function? We talked about it last time. It has to be one-to-one. Excellent. So what I would do is I'm going to just start by looking at the graph of P here. So this is our graph of P of x. Looks like this. Is this one-to-one?
No.
Heck no, right? The horizontal line test, it fails the heck out of it because basically any horizontal line you draw is going to get this guy twice. So what we're going to do is we're going to do something called restricting the domain of P. So we're either going to chop off the left side of P or the right side of P so that the range of our new restricted function is still the same. The only y values we're losing are duplicates. Now, does it matter which side that we chop? No, man, it doesn't. So let's chop this side for the sake of argument. So the way we represent that is we say, okay, where P of x is equal to this, but only for x's that are greater than or equal to 0. So we're only taking like the x's that live over here. And by doing that, we now have a function that's one-to-one, right? So let's look at where this piece plays in when we find the inverse. So we start the same way, right? We add the 4 over, we divide by the 3, we square root both sides. All of this is still the same steps that we did before, so I'm just motoring right through this. This is the place where something happens now. I know for P of x, x is greater than or equal to 0 here, correct? And here we have x equals plus or minus something. Well, can x be minus something if it's always greater than or equal to 0? No. That allows me to drop the plus or minus here. And as a result, what we have now is our P inverse as a function. Alondra? Right, so how is this going to apply to something I'd ask you guys to do? Because I would not ask you to do the domain restriction on your own, right? So if you look at a problem like 46, you see this at the end. All that's telling you is that when you get to the plus or minus bit, you'll be able to drop the plus or minus. That's all that's kind of there for. Billy? Of course. You guys feel okay with that? And that's not an infrequent thing that you'd see. If you took an ACT recently, you would probably run into a problem where they have some like domain condition attached to the function for a reason like this, where it allows you to dump the plus or minus. I mean, I did, but that was like 30 years ago or something. I did not score a 36, believe it or not. To be honest, I don't know, 30 something. I don't remember. It was a long time ago. I was not good at English. I was not good at English.
I got a 32 on reading.
Yeah, I think I got like 33 or 34 on like the math and science stuff. The reading was okay and the English was kind of bad.
The math is like worth more than but not like.
Multiple choice English I always found hard because I'd just be like, I just rewrite the sentence. I don't want to make any of the changes you want. I would just rewrite the sentence because this is bad, period. Yeah. Anyways. Wait a minute, what are we doing here? We should check. So I'm going to just like speed up some of the writing for these checks. Is that okay? So plus 4 over 3. So again, plugging this into P. So P is 3 times the x squared. But instead of x, I'm going to write this square root of stuff, and then minus 4. So when I simplify this, what's the first thing that I need to do? Yep, I deal with the squared, and because I'm squaring a square root, those things just cancel out. That's rad. Well, you could, but I probably wouldn't think about it that way because I just see a times 3 and divides 3. You know? But yeah, you could distribute it in. That wouldn't be wrong to do. And then I just have the plus 4 and minus 4. And I'm done. Make a common denominator and like, it's like, I don't know, just times 3 divides 3. Those cancel. Done. Isn't that nice? Okay, if we go the other way, we're plugging 3x squared minus 4 into P inverse. So we have like our big radical. And then instead of x, we have 3x squared minus 4. And we have the plus 4. And we have over 3. What's the first thing I should do simplifying here? Yeah, inside the radical, the plus 4 and minus 4. Next, I should. No. Not yet. Yeah. Now we have to get rid of the 3's. Again, we have divides 3 and times 3, cancel each other out. Now that we just have something squared underneath, now the radical can cancel. Nathan, if you tried to do the radical there, you'd have this would need to be your result.
Okay.
Which you could do. I would not recommend it because it's like kind of messy.
Yeah.
I would just do like inside out rather than outside in. What do you guys think? Was this check a heck of a lot better than the last one? Yeah. I told you that last one is kind of the worst, or the fraction one was kind of the worst one. All right. Okay. Another inverse. What is this kind of function called? From last year, what would this kind of function be called? Where it has a square root in it, like that. It's a radical function. All right, getting the x by itself. We'll square both sides. And then we'll subtract 5 and divide by 12. And then switchy swappy. And I can just write that as, yeah, I did it in like a minute. You got to realize though, like, I've been doing this job for like 16 years. Imagine taking the same class for 16 years in a row. How good would you be at that?
I can imagine.
And not only are you just taking the class 16 years in a row, you have to stand up and like show everybody how good you are at it for 16 years in a row. Like you're just going to get really good at it. All right. I'm going to skip the check on this one in the interest of time because I want to get to these last two examples. Ooh, this one looks scary. What's weird about this one? The variable is in the exponent. Excellent. All right. So first thing I would do is, can I multiply the half and the 3? Definitely not. Why can't I do that? The exponents are different, right? If they both had the same exponent, you can multiply the bases together. If both of the bases are the same, you can add the exponents, but you can't do different base, different exponent. No dice. So let's just multiply both sides by -2 to get that out of there. And then how do I get that x out of the exponent? What mathematical operation do I need to use to do that? Excellent. I need to use a logarithm. I would not use the natural log in this case, though. We can pick any base of logarithm we want. Now, the natural log will work, but it's inconvenient. The base of the logarithm that I want to pick should match the base of the exponential. So the log that I would use here is log base 3. You guys remember logs from last year? You knew that you needed to use one, which was excellent. That's half the battle right there. So we're going to do that to both sides. Those cancel out because their bases are the same.
The log.
And now we can just divide both sides by 4. Now when I write this, I'm not going to write it over 4. I'm going to write it times 1/4. The only reason I do that is because I don't want it to be ambiguous whether I mean this thing over 4 or the whole thing over 4, because those mean two different things. So I just put the 1/4 out front where it's like clearly the 1/4 applies to the whole logarithm and not just the stuff on the inside. Now that's just something I like to do. You don't have to do it that way, but I kind of recommend it. So if I wanted to check this, I'm just going to check one way because we're getting right down to the end of it time-wise. Is everybody okay with that? And I still have one more example I want to do right quick. Sorry that I'm motoring here. So we have, -1/2 times 3 to the 4 of 1/4 log base 3 of -2x. The 4 times 1/4 cancel each other out. Log base 3, exponent base 3 cancel each other out. And I'm left with just x. Last example. Yeah, what does that ln mean? That's the symbol for natural log, right? And what is the base on natural log? It's the irrational number e, which is like that 2.71 yada, 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 yada number. So I'm going to multiply both sides by 3/5 to get rid of the fraction. And now to cancel out the natural log, I need the exponent base to match the natural log. So that's going to be exponent base e. I'm going to write that kind of absurdly big so it doesn't look like I'm multiplying both sides by e. Rather, I'm making e the base of an exponential for both sides. But the point is that those two things cancel each other out. Then I can add 1 to both sides and divide by 7. And again, I'm going to try to be careful so that it doesn't look like the +1 is in the exponent. And that's all she wrote for us. Swap the x's and y's and rewrite it as a function notation. And we're done-zos. At this point, you guys should be able to do through 56. So that should complete enough to do the rest of these problems. This is going to be the last section of Chapter 1 we're going to do at this time. We're going to come back and do Section 8 of Chapter 1 a little bit later when it's a little bit more relevant. So we're looking at test time probably next week. We'll talk more next class about what to expect and all that jazz. Just giving you the heads up, though, that is in our immediate future.